In the last lecture, we were looking at unidirectional mass, momentum and energy transport in a Cartesian coordinate system. Okay. So, basically we had two surfaces perpendicular to the z direction at z is equal to 0 and z is equal to h. Okay. And in general I could have different concentrations or I could have a situation where the two surfaces had different velocities, okay, in the x direction, okay, and I have to derive a differential equation for the variation of the concentration, temperature or velocity in all three directions and in time. Okay. So, there is a variation in these properties in all three coordinate directions and in time, okay, and we have to derive equations for that. The way we do it is by doing a balance over a differential volume. Okay. Write a balance equation for the fluxes or the total rate of transport, okay, of mass, momentum or energy. Okay. So, okay, of the fluxes, okay, at these two different locations, okay, and the basic conservation condition is that change in mass or energy, okay, is equal to mass or energy in minus mass or energy out plus production in the volume. Okay, there is a conservation condition for mass conservation and energy conservation. For momentum conservation, we have to take a differential volume and find out all of the forces that are exerted on this volume. Okay. Change in energy, sorry, change in x momentum, okay, be careful here, this should be rate of change of x momentum is equal to momentum in minus momentum is equal to plus the sum of forces. And I told you that the rate of momentum in and the rate of the momentum out are the same because the velocity is in the x direction, it is independent of the x direction. Okay. So, whatever is coming in on the left will go out on the right. Forces of two kinds, one is what are called the surface forces, okay, which is basically the pressure force, the pressure force in the x direction acts on the left face and on the right face. Okay, the pressure force on the x direction acts on the left face and the right face. Pressure always acts along the inward unit normal. It is a compressive force. Since there is no variation in the x direction, the magnitude of the pressure on both sides is the same. The pressure on both sides is the same. Direction is opposite, so there is no net force. Okay. The other force is the shear stress. Okay. On the top surface, the unit normal is in the plus z direction. Therefore, the shear stress is tau xz. On the downward surface, unit normal is in the minus Ez direction. Okay. It is in the negative direction. Therefore, this is minus tau xz. Okay. Where Ez is the unit normal in that z direction. Okay. So, I said that the shear stress is positive, is in the positive x is equal to tau xz if it acts at a surface whose outward unit normal is in the z direction. X refers to the direction of the force, z refers to the direction of the perpendicular to the surface, the outward perpendicular to the surface. So, if you reverse the direction of the perpendicular, then the direction of the force reverses. So, these are the surface forces, and then you also have the body force. The surface forces are products of the stress and the surface area. Body force is the product of a force density and a volume, like a gravitational force. So, it is basically proportional to the volume of fluid. Surface forces are proportional to the surface area. Okay. So, we can do this balance for momentum conservation. Okay. And if we do all of this, we get a we get in the end a common form for the differential equation. Okay. Partial of phi Fv by partial t, where phi Fv is the field variable. Okay. Phi Fv is the field variable, temperature, concentration, velocity. Okay. Phi Fv is the field variable. Actually, it should be the densities, the energy density, the mass density, the momentum density. If the density and specific heats are constant, you can also define them as temperature because rho Cp is a constant, and velocity because rho is a constant. These are equal to minus partial of j by partial z plus the source. Okay. Where the field variable, okay, is going to be equal to concentration, temperature and velocity, and the flux is going to be equal to the mass flux, the heat flux by rho Cp. Okay, if I express it in terms of the temperature field, or it will just be the heat flux if I express it in terms of the enthalpy density field. And Vx, okay, this is equal to minus the shear stress, okay, if I express it in terms of the velocity field. Okay. The flux is actually negative of the shear stress in this case. Okay. And then I write Jz is equal to minus the diffusivity partial phi Fv by partial z. Okay. Where this diffusion coefficient is the mass diffusion coefficient for mass transfer, it is equal to the thermal diffusion coefficient for heat transfer, thermal diffusion coefficient for heat transfer. This will be equal to the kinematic viscosity for momentum transfer. Okay. That is the general form. Okay. With that, I get the equation as partial phi Fv by partial t is equal to partial by partial z of d partial phi field variable by partial z plus s. Okay. Where this s is equal to the mass source for mass transfer, energy source by rho Cp for heat transfer, and this is equal to the momentum force density by the density for momentum transfer. Okay. And finally, if this thing is a constant, if the diffusion coefficient is also a constant, then I get partial phi Fv by partial t is equal to d times d square. Okay. for constant diffusivity. Okay. So, that is the general form of the relations. Okay. That is the general form of the relations for heat and mass transfer. Okay. The point to note is that the fluxes for mass and heat transfer are defined positive in the plus z direction. The flux for momentum transfer is defined as positive if it acts on the volume below the surface, so that the outward unit normal is in the plus z direction. Okay. And the constitutive relations are Fick's law, whereas Jz is equal to minus d partial c by partial z, okay, and Qz is equal to minus alpha times partial of enthalpy by partial z, or minus k partial t by partial z, and for momentum transfer it is tau x z, Newton's law, that is equal to nu times partial Vx by partial z. Okay. Okay, so, the negative sign in the expression for the flux and a negative sign and the positive sign in the expression for the relation between the stress and the velocity gradient. And then all of these equations have the same form. Okay. Either this one, if the diffusion coefficient is a function of position or time, and this one if the diffusion coefficient is a constant. Okay. So, we can solve all of these equations all of these problems using the same set of equations, except that we have to change the field variable, change the diffusion coefficient and the source or the force density. Okay. So, this is as far as solving as far as obtaining the conservation equation is concerned for unidirectional transport with variations in one spatial coordinate and in time. Okay. Now, how do we solve these problems? Okay. So, let us go on to looking at solving problems with increasing degree of complexity. Okay. Okay. The simplest problem is to consider steady state constant diffusivity. If I take heat transfer as an example, the conservation equation was that partial T by partial T is equal to alpha partial square plus the source. Okay. So, if I had a single slab of height h, okay, and I substitute T is equal to let us assume that it was at steady state, okay, in which case there is no time variation, and assume that the sources are 0. So, that there is no net source. Okay. Therefore, at steady state in the absence of sources, the differential equation just reduces to d square t by dz square is equal to 0. Total derivative because there is no time variation. Okay. Total derivative because there is no time variation. Okay. The solution of this is just a linear function, t is equal to a z plus b. Okay. That is the solution, okay, for this linear differential equation, and the constants a and b are determined from the conditions that t is equal to 0 here and t is equal to th here. Okay. Okay, that determines the constants a and b. Okay. And you can easily solve this problem, satisfy the constants and get T naught plus Th minus T naught into Z by H. Okay. This is a linear temperature field, okay, with T is equal to T naught here and T is equal to Th here. Okay. So, it is a linear variation of temperature with T is equal to T naught at the bottom and Th on top. Okay. So, this from this you can get the heat flux Qz is equal to minus k dt by dz the total derivative in this case, because the temperature is independent of time, minus K into Th minus T naught by H. That is the heat flux. Okay. And the total heat transfer rate is equal to the heat flux into the area, okay, is equal to the heat flux multiplied by the area. Okay. So, this is equal to minus A K into Th minus T naught. Okay. Yeah. Okay. So, this is a simple problem and it has a simple solution, a linear variation of temperature with respect to position in the z direction, because the second derivative has to be 0. Okay. Let us consider a slightly more complicated case, okay, and that is a composite slab. Okay. Rather than having one material with one thermal conductivity, okay, I consider materials with two thermal conductivities. Okay. So, I have a material with conductivity K2 here, and conductivity K1. Okay. T is equal to T naught, T is equal to Th, okay, and the thicknesses are H1 and H2. Okay. The two slabs have thickness H1 and H2, conductivity is K1 and K2, and the total height, okay, is, this is Z is equal to 0 here at the bottom and Z is equal to H at the top. So, that H is equal to H1 plus H2. Steady state in the absence of any sources or sinks of energy. Okay. So, how do we solve this problem? Okay. First of all, because it is a steady state and there are no sources or sinks of energy, therefore, I require that d square T by dz square is equal to 0 in both slabs. Okay. I require that d square T by dz square is equal to 0 in both slabs. Okay. Let us assume that the temperature here is some intermediate value which I will call as Tf. Okay. Let us assume that the temperature here is some intermediate value that I will call as Tf. Okay. So, in both slabs the temperature has to be linear functions, okay, and therefore, the heat flux in both slabs, okay, heat flux in both slabs is going to be equal to, okay, minus K into Tf minus T naught by H1. Okay. Okay, the temperature in the first slab is going to be equal to, okay, the difference in temperature between H is equal to H1, Z is equal to H1 and Z is equal to 0 divided by thickness multiplied by minus K, because energy goes from higher to lower temperature. Okay. That is the flux in the first slab. Okay. The flux in the second slab is going to be equal to, sorry, I should put a K1 here, okay, minus K2 into Th minus Tf by H2. Okay. So, if I have some other temperature variation in the second slab, this is Tf, this is this is Th. Okay. The temperature here is Th, and Z is equal to H. The difference in temperature across the second slab divided by the thickness. Okay. Recall that the flux is equal to the difference in temperature by thickness. Okay. The flux is equal to the difference in temperature by thickness multiplied by minus K for each slab. K for each slab is different, H for each slab is different. Okay. However, the flux at steady state has to be the same because there are no sources or sinks. If the fluxes were different, there would be accumulation of heat energy at the interface. Okay. If there is to be no accumulation of heat energy at the interface, okay, then the fluxes in the two media in the two slabs have to be exactly the same. Okay. So, the fluxes in the two slabs have to be exactly the same. Okay. So, therefore, I can use this to find out what is this temperature Tf in between the two slabs. Okay. I can use this to find out what is this temperature Tf. Okay. If I take Tf all to one side, okay, I will get Tf into K2 by H2 plus K1 by H1 is equal to K2 Th by H2, okay, plus K1 T0 by H1. Okay. Just rearranging this equation, taking Tf to one side and all other quantities T proportional to T0 and Th to the other side. Okay. So, the temperature intermediate at the junction of these two slabs has to be equal to K1 by H1 plus K2 by H2 whole inverse into K1 T0 by H1 plus K2 T0 by H2. Okay. This gives you the temperature at the junction between these two slabs, okay, Tf. Okay. Recall that we had obtained expressions for the heat flux here, okay, but that expression contained an unknown value Tf at the junction between the two slabs. Everything else was known, the conductivity, the thicknesses as well as the temperature at the boundaries, those were all known. Tf was not known, and we determined Tf from the condition that the flux in those two slabs has to be equal. Okay. Now that we have a value for Tf, we can then calculate the heat flux from, say, this first expression. We can use this first expression in order to calculate the value of the flux. Okay. Okay. So, therefore, Tf minus T0 is equal to K1 by H1 plus K2 by H2 whole inverse into K1 T0 by H1 plus K2 Th minus T0, okay, and I can multiply throughout by this K1 by H1 plus K2 by H2 whole inverse into and you can simplify this expression to get K1 by H1 plus K2 by H2 whole inverse, okay, into K2 by H2 into Th minus T0. Okay. So, this is Tf minus T0 and the flux was equal to minus K1 into Tf minus T0 by H1 whole inverse K1 by H1 K2 by H2 into Th minus T0. And I can further simplify this as minus Th minus T0 by H1 by K1 plus H2 by K2. Okay. You can easily see that this part here can be written as 1 over H1 by K1 plus H2 by K2. Okay. So, this is the expression for the heat flux for a composite slab, okay, consisting of two materials. Conductivity is K1, K2, thickness is H1 and H2. Okay. Now, this expression that I had here, okay, so I can define the resistance to mass transfer, okay, I am sorry, the resistance to heat transfer, okay, the resistance to heat transfer, okay, as equal to minus delta T by Qz. Okay. This is usually defined with respect to the total heat transfer rate rather than the heat flux. Okay. So, for that I just have to write that Qz is equal to A times Qz is equal to minus Th minus T naught by into A by H1 by K1 plus H2 by K2. The resistance is written as minus delta T by Qz. Okay. The resistance of slab I is equal to minus delta Ti by Qz. Okay. And recall that the delta T by Qz, okay, the delta Ti by Qz is equal to H1 by K1A. Okay. The difference in temperature across the first slab divided by the flux, okay, okay, difference in temperature across the first slab when divided by the flux has to be equal to H1 by K1A. Okay. And similarly, the difference in temperature across the second slab divided by Qz was equal to H2 by K2A. Okay. So, you can define the, there should be a negative sign here. Define the resistance as minus delta Ti by Qz, okay, and this has to be equal to Hi by Kia. So, therefore, the delta Ti will be equal to Qz into Ri, which is equal to Qz Hi by Kia. Okay. The temperature difference across each slab, okay, is equal to the flux times Hi by Ki times A. Okay. The heat flux for this series configuration is the same for all of the slabs. The temperature difference is not the same. The heat flux is the same. The temperature difference is not the same. Okay. Therefore, the total temperature delta T is equal to delta T1 plus delta T2 plus etc. plus delta Tn. If I had a configuration with multiple slabs, okay, okay, delta T1 is the temperature difference here, delta T2 etc. delta Tn, okay, and they have different thicknesses H1, H2 etc. Hn. Okay. So, if I have multiple slabs here, okay, with different thicknesses, right, then the temperature difference is the sum of the temperature differences across each of these slabs, okay, which is equal to Qz into R1 plus R2 plus etc. plus Rn for multiple slabs. Okay. Therefore, Qz is equal to delta T by R1 plus R2 plus etc. plus Rn, where the temperature difference across the entire slab is delta T, okay, where delta T is delta T1 plus delta T2 plus etc. plus delta Tn. Okay. So, therefore, this heat transfer resistance just adds up, okay, as you have multiple slabs, right. The total resistance is equal to R1 plus R2 plus etc. plus Rn, okay, for the heat transfer across multiple slabs, where the resistance for each slab is the thickness divided by the conductivity divided by the area. Okay. Note that as the thickness increases, resistance increases, okay, because you have to transfer heat across a thicker medium. When conductivity increases, the resistance decreases. As the conductivity increases, the heat flux increases for a given temperature difference, resistance decreases, and as the area increases, the resistance decreases. Okay. Okay. So, by defining this heat transfer resistance across multiple slabs in the series configuration, I can get the total resistance as the sum of the individual resistances, and the heat flux is the total temperature difference divided by the total resistance. For a series configuration, the total resistance is the sum of each of these individual resistances. Okay. So, this is for a case where there is no source and it is a steady state, and therefore, the temperature or in general the field variable, okay, in more complicated problems of in problems of mass or momentum transfer as well, the field variable, the second derivative has to be 0. So, the field variable has to be a linear function. If the diffusion coefficient is a constant, no sources and no time variation. Field variable is a second order differential equation, d square field variable by dz square equal to 0. Field variable is a linear function of z, and if you have multiple slabs, the flux can be written, or the total transfer rate, okay, can be written as the difference in the field variable divided by the total resistance, where the total resistance is the sum of the individual resistances. Individual resistances are thickness divided by the conductivity divided by the area, or thickness divided by diffusivity divided by area, okay, as the case may be, whether you pose it in terms of temperature or enthalpy density. Okay. So, this is for a series configuration. Okay. We will continue this, summarize this and discuss a parallel configuration in the next lecture before we go to consider cases where there is a source within the channel. Okay. So, where there are sources, this does not apply. Okay. And similarly, if there are variations in the diffusivity, this does not apply. We will examine those cases, continue in the next lecture. I will see you then.